Good morning friends, I welcome you all for my YouTube channel. So previous sessions we were discussing about matrices, we have discussed many things, lot of problems we have solved, many examples we have solved, right? So we have also completed 3 exercises. Okay, so the next topic and the last part of this chapter is elementary transformation and inverse of a matrix, right? So these are the last 2 topics. First one is elementary operation or transformation of a matrix, and after this there is a small topic called as inverse, right? But on inverse, right, many problems will come, right? So you should apply these properties or transformations to get the inverse of matrix. Okay, so we are having basic 3 types of transformations, right? So for the 3 types of transformations will be converted into 6 type, right? So 3 for rows and 3 for columns. So basically there are only 3 operations. So if you are applying them for rows and columns, so you can consider them as 6 transformations. Okay, so one by one we will see. First 2 are here. We will see them. What are the 2 transformations? First 2 transformations. Once we are aware of these 2 transformations, then we will proceed to the third one. Okay, so interchange of, first one is interchange of any 2 rows or columns, right? You can interchange the rows or column, but one thing is there: if you are interchanging rows, you should interchange 2 rows. If you are interchanging columns, you should interchange 2 columns. You cannot interchange row and column. You cannot interchange row with column. So you can only interchange row with row or column with column. So this is interchange of any 2 rows or columns, right? So how do we interchange? When we interchange is just replacing, right? So what is the symbolic representation of that? Because in every step we cannot write we are interchanging first row with first column, third row, second row with third row. We cannot write those things, right? So we need some symbolic language or symbolic abbreviation for that. Okay, so interchange of any 2 rows or columns, how that will be there? If ith row, I and jth row are interchanged, if ith and jth rows are interchanged, that can be symbolically represented as Ri interchanging with Rj. Here the arrow mark is on both sides, though. So what is the meaning of this? Ri is interchanged with Rj. And if you are doing it for column, so ith column with jth column, then it can be abbreviated or it can be symbolically represented as Ci interchanging with Cj. So that symbolical meaning will be the rows or columns are interchanged, and that will be represented as arrows with both sided arrows, right? A line with arrowhead on the both sides. If that if you write this one, then it is understood that Ri is ith row is interchanged with jth row. If you write this way, ith column is interchanged with jth column. So we'll see one example. If A is a matrix, it is of a matrix of order 3 cross 3. So 1 3 5 7 9 8 6 4 2. Then if I am interchanging first row and second row, it is not compulsory that only first and second row should be interchanged. You can interchange first and third, you can interchange second and third also, right? So here I am interchanging first and second rows. Then how will I represent that one? R1 is interchanged with R2 this way, right? R1 interchanged with R2 on A. I am applying R1 interchanging R2 on A. Then what happens to A? So first row and second row will be interchanged. What is first row here? 1 3 5. That should be on the second row. Here you can see 1 3 5. What is second row here? 7 9 8. So that will be in the first row. So first row becomes second row becomes first row. If it is for R1 and R3, then first row comes on third row will go on first row. Is that clear? So this is how the transformation will be there. Okay. So next one. So I hope the first transformation is much clear. So let's move on to the next one. So multiplication of elements of any row or column. Multiplication of elements of any row or column by a non-zero number. Right? Multiplication of elements of any row or column by a non-zero number. Okay. So multiplying each element of ith row, example is ith row, you can take any row, by k, ith row by k. K is any number which is not equal to 0, right? K is any number which is not equal to 0. So what we are doing here, we are multiplying a non-zero number to any row or column. Okay. So multiplying each element of ith row by k, where k is not equal to 0. How do we represent that? R1 changes to KR1. R1 changes to KR1. Observe the difference in symbol. Here the arrowhead is on both sides. Here the arrowhead is on the right side only. Okay. So here R1 interchanges with R2. Here R1 changes to KR1. R1 changes to KR1. Right. And if it is for column, then CI changes to KCI. Here Ri changes to KRI. Here Ci changes to KCI. Okay. So generally we have taken as ith row. If it is first row, it will be R1 changing to KR1. If it is second row, it will be R2 changing with KR2. Okay. So that is how it will be there. Okay. For example, let B be a matrix. It is of order 3 cross 3. Then I want to multiply a number 2 to each and every element of column 1. Each and every element of column 1 is multiplied by 2. Okay. So then how it will be represented? Column 1 changes to 2 into column 1. Column 1 changes to 2 into column 1. What happens here? If I multiply each and every element of column 1 by 2, 7 becomes 14, 1 becomes 2, 4 becomes 8. Remaining numbers will be as it is. That is to be very much clear. So the operation will be applied strictly on the particular row or column. If I am mentioning R1 and R2 are interchanging, only there will be changes in row R1 and R2. The row R3, the third row will remain unchanged. You can see here 6, 4, 2. Right? If I am applying for second and third row, first row will remain unchanged. If I am applying to first and third row, second row will be unchanged. Same is the condition with column also. Whatever rows or column are into consideration, only those things will modify. Remaining everything will remain as it is. Okay. So here also I am multiplying 2 to column 1. I am multiplying 2 to column 1. So only entries in column 1 will change according to this condition. Remaining everything will remain as it is. Is that clear? So now what you should do is, carefully you go through this video. Okay, carefully you go through the video, pause this video and make a note of this. Okay, make a note. So friends, so those two properties already you have taken, I hope. Let's move on to the third one. So what is this third one? So it states that the addition of elements of any row or column, the addition of elements of any row or column, the corresponding elements of any row or column multiplied by a non-zero number. Right? What is it saying? The addition to the elements. Addition to the elements of any row or column. So to any row or column, if you are adding elements, right? So to any row or any column, to elements of any row or column, if you are adding the corresponding elements of other row. Is that clear? So don't get confused here. To elements of any row, we have first row, second row, third row. That way we have n number of rows, right? So to elements of any row or column, right, if we are adding the corresponding elements of other row or column, corresponding elements of other row or column, that too multiplied by a non-zero number, that too multiplied by a non-zero number. For example, for the elements of first row, if you are adding elements of second row, how should you add? The corresponding elements should be added, right? So A11 and A21, A12 and A22, A13 and A33. So to any elements of first row, if you are adding the corresponding elements of second row, that too multiplied by the non-zero constant, then this property can be applied. Then how do you represent that? Ri changing to Ri plus Krj. Ri plus Krj. What is this Ri? Ith row. To this ith row we are adding elements of jth row. To elements of ith row we are adding the elements of jth row. But not just the elements of jth row. K multiplied to elements of jth row. First you should multiply k to elements of jth row and you should add them to ith row. Then if that is the case, then we can represent it as Ri changing to Ri plus K Rj. If it is for column, Ci changing to Ci plus K Cj. Once again I repeat. So to any row or column, to elements of any row or column, if you are adding corresponding elements of any other row or any other column multiplied by a non-zero constant, then it can be represented as Ri changes to Ri plus Krj, or if it is for column, Ci changes as Ci plus K Cj. Let us understand this one clearly by a simple example here. Let C is equal to 4, 6, 8, 2, 3, 1 and 5, 7, 9. Okay. Let A be equal to 4, 6, 8, 2, 3, 1, 5, 7, 9. So what is the operation I am applying here? Then applying R2 changes to R2 plus 3 R1. R2 changes to R2 plus 3 R1. What I am doing here, to each and every element of R2, I am adding corresponding elements of R1 multiplied by 3. Is that clear? So for each and every elements of R2, the corresponding elements of R1 are added multiplied by 3. So first I am multiplying 3 to R1 and adding those corresponding elements to R2. Right? Then see, R2 is changing. So R2 only will change. R1 and R3 will remain as it is. So what is there in R1? 4, 6, 8. I write it as 4, 6, 8. Now R2 should change. R2 should change as what? R2 plus 3 R1. Right? So R2 is having what values? A21, A22 and A23. So what will be new A22 value for us? Right? See, R2, that is 2 plus 3 times of R1. 3 into 4. So what is the value? 2 plus 12, that is equal to 14. Now what will be? Sorry, A21, this is A21. What will be A22? Right, this is 3 here. According to that, R2 here it is 3 plus 3 times of what is R1? 6. So this will be 3 plus 18. Right. So what is 3 plus 18? 21. Similarly, last one, A23. R2 is 1 plus 3 times of R1. 3 times of R1 is 3 into 8. So this will be 1 plus 3 into 8 is 24. So this will be 25. So in second row, what are the elements we are getting? 14, 21 and 25. So 14, 21 and 25. So second row will change as 14, 21 and 25. And third row will remain as it is. So I hope this thing is clear. So here what we are doing, we are adding for any row or any column, we are adding some other elements of some other row, and that some other row will be multiplied with some constant. After multiplying that constant, we are adding to our required row. Here what is the constant? 3 is our constant. So 3 is multiplied to row 1 and then it is added to row 2. Here 3 is multiplied to row 1, then it is added to row 2. Then you can see what happens to row 2. 14, 21 and 25. Initially they were 2, 3 and 1. Now they have changed it to 14, 21 and 25. Is that clear? So I hope the thing is clear here. So you pause this video, take the notes down. Okay friends, let's move on to next topic, that is invertible matrices. So what are invertible matrices? The matrices which are having inverse version of the same thing, right? If A is a matrix, if it is having inverse of inverse, then we call it as invertible matrix. Okay, so one more condition, for any matrix to be inverse, it should be a square matrix. So if A is a square matrix of order m, and if there is another square matrix B of same order m, such that A into B is equal to B into A is equal to I, A into B is equal to B into A is equal to I, then B is called inverse of A and is denoted by A inverse, right? So if there is a matrix, square matrix A of order m, and also there is one more matrix, that is square matrix B of same order m, then if A into B is equal to B into A is equal to I, if A into B that is equal to B into A, then that it is equal to I, then B is called inverse of A. B is called inverse of A, or A can be said as invertible matrix, right? If there are two square matrix of same order, right, and this condition is satisfying, A into B is equal to B into A is equal to I, then B is said to be a square, B is said to be inverse of A, right, or A can be said as invertible matrix. Here B is inverse of A and vice versa, A is also inverse of B, right? So if this condition is satisfied, A will be inverse of B and B will be inverse of A. Okay, so let us check. Let A is equal to 2, 3, 1, 2, a square matrix of order 2 cross 2, and let B is equal to 2, minus 3, minus 1 and 2. Then what will be the value of A into B? Multiplication, first row with first column, 2 into 2, 4, 2 into minus 1, 3 into minus 1, minus 3. Then first row with second column, 2 into minus 3, minus 6, 3 into 2, plus 6. Then second row with first column, 1 into 2, that is 2, 2 into minus 1, that is minus 2. And for second row with second column, 1 into minus 3, 2 into 2 will be 4. So now what is 4 minus 3? 1, minus 6 plus 6 cancels, 2 minus 2 will cancel. 3 minus 3 plus 4 is 1, right? So what we got here? 1, 0, 0, 1. This is nothing but I. So here A into B, we got it as equal to I, right? So let us check B into A. B is 2 minus 3 minus 1 2, and A is 2 3 1 2, right? If I multiply 2 into 2 is 4, minus 3 into 1 is minus 3, so 4 minus 3. Now first row with second column, 2 into 3 is 6, minus 3 into 2 is minus 6. Now second row with first column, minus 1 into 2 minus 2, 2 into 1 plus 2. Now second row with second column, minus 1 into 3 minus 3, 2 into 2, 4. Right, now 4 minus 3 is what? 1. 6 minus 6 is 0. Minus 2 plus 2 is 0. Minus 3 plus 4 is 1. So what we got here? 1, 0, 0, 1. There is nothing but I. So we got A into B as equal to I, B into A as equal to I. Right? Then we can say that B is inverse of A, or A as inverse of B. If B is inverse of A, I can write B is equal to A inverse. And as A is inverse of B, I can also write A is equal to B inverse. Is that clear? So I hope the things are clear here. So what we should understand is, to have a inverse, a matrix should be a square matrix. And inverse will also be a matrix of same order. If A is of order m and B is its inverse, then B also will be of the order m only. Okay, there will not be any difference in that. And to be an inverse, definitely it should be a square matrix. A rectangular matrix cannot have any inverse. Okay, so you can take any example. If this any other matrices, if this condition is satisfied, then they will be inverse of each other. Okay, so now we pause this video and take the notes down. Okay friends, I hope you all understood and taken on the previous things which were there on previous slide. So let's move on to next topic. Okay, that is on the same inverse, let us try to prove these theorems. There are two theorems, theorem 3 and theorem 4. First one is uniqueness of the theorem, which states that if any matrix A is having its inverse, then that inverse is unique. Okay, so if there is certain matrix, right, and if it is having certain inverse, right, so if there is a matrix with inverse, then that inverse is unique for particular matrix. Okay, that means one matrix can have only one inverse. One matrix can have only one inverse. Then how to prove that? Okay, how to prove that the matrix is having only one inverse? We cannot go on trying everything, right? So first we have to consider that there is a matrix which is having more than one inverse, right? There is a matrix which is having more than one inverse. That is to be our consideration at the initial stage. Then prove that all those matrices, all those inverses are equal. For example, let A is equal to Aij be a matrix of order M. Let this A be a matrix of order M. Okay, and let B and C be the inverse of A. So what we are considered? We have considered a matrix Aij. It is a square matrix, right? So of order M. Of order M means definitely it is a square matrix. Okay. So let A is a square matrix of order M, and as per our statement it should have only one inverse, right? As per our statement it should have only one inverse. To prove that, initially we will consider that it is having two inverses. It is having two inverses. That's what we have considered here. B and C be inverse of A. Now our job is to prove that B is equal to C. If B is equal to C, then it means that it is having only one inverse. We have considered that there are two inverse and both are equal. Then that means that A is having only one inverse. So to prove that A is having only one inverse, initially we have considered it has two inverse, and then we are proving it both are same. Okay. Now as B is inverse of A, I can write A into B is equal to B into A is equal to I. In previous thing when we started with inverse, we have seen that we have already proved with example that A into B is equal to B into A is equal to I when B was the inverse of A. Similarly, if C is inverse of A, then A into C is equal to C into A is equal to I. A into C will be equal to C into A will be equal to I. Now I can write B as equal to B into I. What is I? It is the identity matrix. I is an identity matrix. So what is the property of identity matrix? If it is multiplied to any matrix, the value of that particular matrix will not change. If it is multiplied to B, B remains as B only. You can take the value of I as 1. So 1 multiplied to anything will remain as same matrix only. Right? I multiplied to B will remain as B. So B can be written as B into I. Okay. But what is B into I? Right? From equation 2, I can write I as equal to AC. I can write I as equal to AC from equation 2. This can be written as B into A into C. The bracket can be shifted, this distributive law, right? So bracket can be applied to B into A and C can be kept outside. What is B into A? I, and C as it is. So what is I into C? That is C. Therefore B is equal to C. Therefore A is having unique inverse. A is having what? Unique inverse. Here we have proven that B is equal to C. So we can say that A is having only one inverse. I hope this one is clear. Okay. So we'll move on to the next theorem. What is that one? If A and B are invertible matrices of same order, then AB whole inverse will be equal to B inverse into A inverse. It states that if A and B are invertible matrices, of same order, then A into B whole inverse is equal to B inverse into A inverse. So let us prove this result. Okay. I can write AB into AB inverse as equal to I. Right? Why? Because A into A inverse is equal to I. As A into A inverse is equal to I, A is a matrix, so matrix multiplied by its inverse is equal to I. So here A into B is also a matrix. If A is a matrix and B is of matrix, then A into B will also be a matrix. Right? If A into B is matrix, then A into B inverse is inverse of that one. So matrix multiplied by its inverse will be equal to I. That is the standard result. Right? So now AB into AB whole inverse is equal to I. Now I will multiply A inverse to this. Multiplying A inverse on both sides. What do we get? A inverse into AB into AB whole inverse is equal to A inverse into I. So multiplying A inverse on the both sides, A inverse into AB whole inverse is equal to A inverse into I. Now apply distributive law here. I can write A inverse into A, B outside, AB inverse is equal to, what is A inverse into I? There is nothing but A inverse. Okay. So I have shifted the bracket. Okay. So now what is A into A inverse? That is I. Okay. A into inverse is equal to I. So I substituted that bit I. B as it is, AB whole inverse, and A inverse as it is. What is I into B? Anything I multiplied by anything will remain as it is. I into B is B. B into AB whole inverse is equal to A inverse. Now once again apply distributive law here. Shift the bracket. B into A. Sorry. Now multiply throughout by B inverse. Multiply throughout by B inverse. On both sides, what do we get? B inverse into B into AB whole inverse is equal to B inverse into A inverse, right? So multiplying B inverse on both sides, B inverse into B into AB whole inverse is equal to B inverse into A inverse. Now what is B inverse into B? So B inverse into B into B inverse is equal to B inverse into B is equal to I. So this will be I why? Because A into A inverse is equal to A inverse into A, that is equal to I. A into A inverse is equal to A inverse into A is equal to I. Similarly, B into B inverse also will be equal to I. Why? Because A into A inverse is equal to I. So B into B inverse also will be equal to I. Okay. Now what is I into AB whole inverse? That is AB whole inverse is equal to B inverse into A inverse. Right? So if I neglect I can write AB whole inverse is equal to B inverse into A inverse. This is how we need to prove this result. Okay, I hope the derivation is very much clear to you. So now you pause this video and take the notes down. So friends, I hope both the derivations are very much clear to you people. So what you need to do is go through the video again and again. So practice many problems, as many as problems possible. Alright. So try to prove these results by taking different examples. You code the matrix by yourself and try to prove the result. Definitely you will get the result. If ever you get any difficulty, you can comment me in the comment box. Okay. So we'll stop today's session here. In upcoming sessions, we'll continue with the inverse of the matrices. So next topic will be finding out the inverse of matrix using elementary transformations. So elementary transformations we have started today. I have explained what are the three types of elementary transformation, 3 for rows and 3 for columns. Total 6 elementary transformations I have explained. So we will use those elementary transformations and find the inverse of any matrix. Okay. So we'll stop this video today and we'll continue in the next session.